These are your instructions. In general, you just need to follow the PowerPoint. Please make sure the sound is turned up on your device so you can hear the narration. Your instructions are in yellow boxes on each slide. If a slide asks for homework, don't forget to send it in via Show My Homework, and if a slide asks for Educate to be completed, don't forget to do it by the date given.
These are our objectives. By the end of the lesson, you should be able to draw velocity time graphs and extract information on lines and slopes. You should be able to determine acceleration from a velocity time graph, and you should be able to calculate the distance traveled by looking at a velocity time graph. Throughout this lesson, you need to be very careful that you know exactly what kind of graph you're looking at. A problem can arise when you're looking at both distance time graphs and velocity time graphs because they look very similar and they're easy to confuse. However, the information on them is entirely different. For a starter activity, have a look at this distance time graph, the kind of graph that we looked at in the last lesson, and see if you can label the various points of the graph and try and remind yourself what that information means. Check your answers on the next slide when you're ready. Now, the kind of graphs we're going to look at today are velocity time graphs. And I will say again, be very careful that you know which graph you're looking at, because though they look the same, the information contained in them and the meaning of the slopes and the lines is totally different for each type of graph. So, velocity time graphs describe the motion of an object. Time goes on the x-axis as before, but this time velocity goes on the vertical y-axis. Now, there are two ways you can be asked to work with this kind of graph. You can be given a graph and you have to extract the information from it and describe the motion of the object. Or you can be given the motion of the object in written form and asked to construct the graph. So you need to be absolutely clear on what each part of the graph is showing. So let's have a look at a velocity time graph. The first thing you want to do is start with some axes. Now, on the x-axis, I've got time in seconds, just as we had in previous graphs. But this time, instead of distance, I've got velocity up the vertical y-axis. So let's have a look at a journey plotted onto this graph. Now, the first part of the journey shows this. Time is increasing along this axis, and velocity is increasing. Now, we know that if an object's velocity is increasing, we know that it is accelerating. The fact that it's a straight line tells us that the acceleration is constant or uniform. Now, the second part of the journey is a horizontal section. Now here you should look at the graph and you should be able to interpret it as follows. Time is increasing across this axis, but the velocity is no longer increasing. The velocity is constant at 10 meters per second. So now we know that this section of the graph shows a steady velocity. Here in the next part we have a curved section. Time continues to increase, but the gradient, the slope, is becoming steeper. That tells us that the acceleration is increasing. Here we have another horizontal section which represents again a steady velocity. Time is increasing this way, but the speed stays at 20 meters per second. Notice that the speed or velocity is constant, but it's higher here than it was here. And then finally, we have a downhill slope. Now, the slope and the fact that it's a straight line tells us that it's an acceleration, but this time it's a negative acceleration, what we would call a deceleration. And the fact that it's a straight line tells us that it's a constant or uniform deceleration. And it finishes here at 130 seconds when the speed or velocity is back to 0. So that means at this point, the object is no longer moving. You need to be able to read a graph like this or construct a graph like this given the information. This is the key information from our graph. The gradient tells us the acceleration. The flat sections tell us that it's moving at a steady speed or steady velocity. The steeper the graph is, the greater the acceleration is. An uphill slope tells you its acceleration in that the speed is increasing. A downhill slope is the opposite. The object is slowing down. It is decelerating. And a steepening curve is increasing acceleration, and a flattening curve is decreasing the acceleration. We can use velocity time graphs to calculate acceleration. And this should be clear to us because we've already worked out acceleration using a formula. Acceleration is equal to the change in velocity over the time taken. Well, we know on a velocity time graph, we can find the change in velocity for any part of the journey, and we can read the time off it. So the graph can be used to calculate the acceleration. All you have to do is work out the gradient or the slope of the part of the journey that you're interested in. So let's return to our journey, the one that we've drawn the graph for, and let's see if we can calculate the acceleration for the first part of the journey. So I've reproduced that first bit of the graph here for you, and it's this slope that we want to work the gradient of because that will tell us the acceleration for that part of the journey. So using our formula, we know that acceleration is the change in velocity divided by the time taken. And the way we noted it before was A equals delta V divided by T. So reading from the graph, the change in velocity, now that's equal to the final velocity minus the initial velocity. Well, this is the part of the journey we're interested in. The final velocity is 10 meters per second. The initial velocity is 0. So 10 minus 0. And the time is from here to here, which is 30 seconds. So if we put in our figures, 10 divided by 30 gives us an acceleration of 0.33 meters per second squared. Now let's see if we can work out the acceleration for the final part of our journey. Now again, I've drawn that final part of the journey here for our convenience. Again, acceleration is equal to the change in velocity divided by the time taken. So the change in velocity is delta V, the time is t. Here, the final velocity is 0. The initial velocity is 20 meters per second, and it's this section that we want to work out the gradient of. And the time is read across the x-axis from 110 there to 130, which is 20 seconds. So final velocity 0 minus initial velocity 20 divided by time 20. If you substitute your figures in, that gives you minus 20 over 20. Put that into your calculator, gives you minus 1 meter per second squared. Now the fact that the acceleration is negative is nothing to worry about. That just means it signifies that it's a deceleration. The object is slowing down. And that should be obvious to you from the graph because it starts at 20 meters per second and it ends at 0 meters per second. So it must be slowing down. Now, on a velocity time graph, we can work out the distance traveled by the object if we can work out the area under the graph. Now, you can do this for the whole journey, or you can do this for a part of the journey. So let's start by drawing a journey onto these axes. So we'll start with a period of constant acceleration, where the velocity increases. Then we'll have a period of steady velocity, and then we'll have a period of constant deceleration where the velocity is gradually reduced back to zero. Now, the kind of question you often get is phrased like this: work out the distance traveled by this object in the first 70 seconds of the journey. So now we're not interested in the whole journey, just the first 70 seconds, and we want to work out the area under the graph for those first 70 seconds. Now, the shape under the graph looks complicated because it is this shape. But what we can do is we can divide it up into a square and a rectangle, and then it'll be very easy for us to work out the area. So we're interested in this triangle and this rectangle. So here I've reproduced that part of the journey that we're interested in, and we want to work out the area under this triangle and this rectangle. So for the triangle, the area of a triangle is given by half times base times height. So the base is here, 40 seconds, and the height is here, is 15 meters per second. So the area of that part of the journey is half times 40 times 15 is 300 meters. Then we're interested in this rectangle. The area of rectangle is given by base times height, which is from the graph 30 by 15, which is 450 meters. So now we know the area here for the triangle and here for the rectangle. We just need to add them together, gives us a total of 750 meters traveled. And you can do this for any graph, providing it has straight lines, and you can divide it into regular shapes that you can work out the area for. Now the situation gets a bit more complicated if you're looking at a case where the acceleration is not constant. So a curve shows you an acceleration which is not constant, which is not uniform. But you can still work out the distance traveled if you can work out the area under it. Now you can do this mathematically, but it's quite difficult. So another way you can do it is by counting squares. So for instance, if I was asked to work out the distance traveled between 30 and 50 seconds for this object, I would go through this process. First of all, I would look at a single square. Now, a single square is 1 unit high, 10 units across. So each of those represents 10 meters. Then what I would do is count the number of complete squares in the part of the journey that I'm interested in. So I would go 1, 2, 3, 4, 5, 6. So there are 6 complete squares. Then I would look at all the partial squares. Now this one is almost complete. There's a little bit there that would add together to make a complete square. Then that one and that one would add together. That one and that one would roughly add together. So if I add up these 6 partial squares on the curve, the 6 partial squares along here, then they would add up to about another 3 squares. So now the total number of squares underneath the graph between 30 and 50 seconds is 9, and you know that each square represents 10 meters. So your estimate, and it isn't 100% accurate, but your estimate is that the distance between 30 and 50 seconds is 90 meters, because that's roughly the area underneath that section of the journey. Now, throughout this lesson, I've asked you to be very careful to recognize the difference between distance time graphs and velocity time graphs. So just to make sure we have all of that information in one place, can you use the information from the last lesson to fill in this column for distance time graphs, and the information from this lesson to fill in this column on velocity time graphs, and put the whole table complete in your books? Your final task for this lesson is to send a picture of your completed table, the one comparing distance time graphs and velocity time graphs, to Mr. Rahman by the 12th of June. Thank you.